So a student asked me to do a video on this question here. This is a question from one of the new papers. It's to do with one of the practicals. Quite a difficult question, 6 marks, asking you to explain essentially how to do this practical. And I think a lot of students don't totally understand what is even happening in this experiment. So let's go through it. So it says, describe how you would carry out an experiment to turn the enthalpy solution of anhydrous magnesium chloride. So we're trying to work out delta H for this reaction here. Now, if you look at this equation, this reaction here, you've got a solid, magnesium chloride, being added to a liquid water, forming another solid. Now, we know that chlorides are soluble, so when you add magnesium chloride to water, it should dissolve. It shouldn't form a solid. So this equation doesn't really make any sense. Basically, this reaction is not feasible. But we can still work out the enthalpy change theoretically by creating an enthalpy cycle. So what we do is we take this equation here, because we know that Hess's law states that the enthalpy change for a reaction, delta H, is independent of the route taken. So we can take a different route. We can turn it into something else. So if we add water to it, this time not just 4 moles of water, but this time we add excess water. So let's write that down, plus excess water. Okay, and we'll put that over the other side as well. You have to have everything balanced, obviously. Oops. So if we add excess water to this side, it's going to form magnesium chloride aqueous. Now, this is a reaction we can do. We just add water, we get some water, and we add magnesium chloride to it, and we measure the enthalpy change. We can measure the temperature quite easily. We can work out the moles quite easily. Should be quite easy to do. And the same, this one, magnesium chloride with the water in its structure, we could do the same thing. We could add excess water to it. And we could quite easily do the measurements and work out the enthalpy change for this one. So say we work out this one. Let's call this one number 1. This is like enthalpy change number 1. And we'll call this one number 2. We can now use these enthalpy changes to work out delta H. So delta H. So remember, Hess's law states that the enthalpy change is independent of the route taken. So we're starting here. This is the start. And we're finishing here. So as long as we start at the start and finish at the finish, the enthalpy changes should be the same. So we can go the quick way. So the quick way is this way, delta H. We just jump straight from the start to the finish. Or the more longer way is we start at the start, we go down to here, and then we go up to the finish. So these enthalpy changes should be the same. Let me do this one in blue. So there's the black quick route, or we can go down to here and then up to here. So therefore, the black route, delta H, is going to be equal to the longer route, which is, can you see how this red arrow is going the same way as this blue arrow? So that's plus the enthalpy change number 1. And then can you see how this blue arrow is going the opposite way to this green arrow? So it's minus the enthalpy change number 2. So that's the sort of concept of why this works. So we can do the experiment and work out delta H, enthalpy arrow 1, the red arrow. We can do another experiment and work out the green arrow, and we can use those to work out this unfeasible reaction, delta H. Okay, so how do we get all the marks? Explaining the method. So the method for this experiment would be that you need to measure out the excess water. So I imagine that about 100 cm cubed would probably do. Measure out 100 cm cubed of water. Must state what you're using 100 cm cubed measuring cylinder. Should work. Okay, 2. What do we need to do next? We need and place into insulated cup with lid. Okay, so that's over here. Next, we need to weigh out our solid. That's our anhydrous magnesium chloride. So 3, weigh by difference. So that means where you weigh initially and then you pour it into the cup. So you pour it into a separate container. Actually, we would pour it directly into the cup, and you then remeasure the weighing boat to see how much you actually added. So weigh by difference, 0.8 grams of anhydrous magnesium chloride. So step 4, we would then measure the temperature every 30 seconds. Graph. This is going to be, I believe this is an exothermic reaction. So magnesium chloride, yeah. So we'll have time along the bottom. That's in seconds. And we'll have temperature on the y-axis. Measure that in Celsius. So initially we'll measure the temperature of the cup. We should have probably said that actually. We should probably say that before here. So before adding solid, measure temperature of water for, say, 4 minutes. This is just to get a sort of baseline reading of what the temperature is of the liquid. Okay, so we've got a baseline reading there, and then we add the solid, and obviously the temperature will start to increase. Okay, the reaction's going on, it's starting to increase, and then eventually the reaction's going to stop and the temperature will start to cool down because obviously the cup is going to cool down. Eventually it will go all the way. I mean, we don't need to go all the way, but it will go all the way, hopefully, or should you go back to room temperature, and then at room temperature it will level off again. Okay, we don't need to go that far, that measurements, because all we're trying to do, the reason we record it after the experiment's finished is we're trying to get the gradient, the cooling gradient, because during the experiment, so here's the experiment hasn't finished, finished. It's heating up due to the reaction, but it's also cooling down due to the liquid just losing energy to the surroundings. And what rate is it cooling down? Well, it's cooling down by this rate. So then we can extrapolate this line and work out, well, what happens if it wasn't cooling down? Say the reaction all occurred instantly, okay, what temperature would it have reached to? And we can extrapolate this up to the time that we added the solid. So we added the solid, say, here. And the difference between these two lines, these two extrapolated lines, gives us the temperature change, or gives us an estimation of the temperature change if the reaction happened instantly and there was no time for it to cool down. Okay, so that's delta T. And then we can place that into our equation Q equals mc delta T. So M is the mass of the water we heated up, 100. C would be the heat capacity of water, so 4.18. Delta T will be whatever we measured here. Let's say it's 40 degrees, so times 40. Okay, this will give us Q, which will come out in joules. Let's call that X. So we've got X joules now. Okay, we can then take that over to this equation, delta H equals joules, so it equals Q, but this time this has to be in kilojoules. Okay, so to convert that into kilojoules, we can just simply divide by 1,000. Okay, so we can divide by 1,000. We could do it before we put it in the equation, and we divide it by moles. Now this is the moles of our thing, which is the limiting factor, which is this 0.8 grams of magnesium chloride. So work out the moles of that. So moles equals mass over mR, so it's quite easy to work out that. We can see how the mass is 0.8, the mR is, well, whatever it is, I mean, that's 23 plus 35.5 times 2. Okay, so we can work out that. So we've got the moles, and we've got Q, so therefore we can work out delta H, and that will give us, this is delta H, this is delta H1, this is the red arrow here. So we've now worked out this one here. We can repeat the whole lot again to work out number 2, but this time we'll be doing it, we're repeating the same experiment, but this time we'll be adding, rather than anhydrous magnesium chloride, we'll be adding the hydrated magnesium chloride. Do the same mass, everything the same, and work out delta H for this one. And that's how to do the question.